Hello, dear friends, and welcome back to our Introduction to Statistics. And in this particular video, we're going to begin Week 6, Introduction to ANOVA, and where we're comparing three or more populations. Last series, we looked at the t-test, which is the comparison of two populations. And I point out to you that a t-test is in fact an ANOVA where you only do two populations. So the ANOVA could actually be two or more populations, but for our purposes, we're going to look at three or more. Now, you will recall the steps of hypothesis testing. Using a 6-step plan, you state the null hypothesis, the alternate hypothesis, establish the critical value, and you find the test research statistics. You draw your conclusion and you write your finding into statements. We utilize the structure of hypothesis testing to examine a claim, and based on our sampling techniques, we will either reject the claim or fail to reject the claim. And I point out to you that in hypothesis testing, we have only two options. We either fail to reject H0 or we reject H0. Those are the only two options that we have. And what we did last week was about two populations, and before that we looked at a claim about one population. Suppose we want to compare three or more populations to determine if they are similar or if they are different. Now, here's a diagram comparing three or more curves. Now, I'm very proud of this diagram. We have group 1 in this diagram where we have, which runs here in its normal distribution, group 2 here in group 3. We might have these three distinct populations and we want to look at them to see if the means differ statistically. Now here's comparing three or more curves. We're looking at 4 curves. We have a group 1, a group 2, a group 3, and a group 4. I'm also proud of this little diagram that I worked on for you. If we were to want to examine 50 different populations at the same time, we could certainly do so. It might make interpreting our results a little bit more difficult, but when we have 3 or when we have 4 groups, interpreting the results really isn't too difficult. Now, the test that we're going to use is called analysis of variance and shortened to ANOVA, A-N-O-V-A. And ANOVA requires 3 things in the protocols before it has actual meaning. The first of those is independence. The populations that we're examining must be independent of each other. Normality, they must be normally distributed, and then they must have homogeneity of variance. In other words, the curves have similar standard deviations, and these protocols must be satisfied for the ANOVA to have meaning. Now, I do want to point out to you that what if you fail to really establish homogeneity of variance at a good level? Well, what you would do in your study, you might proceed to do the ANOVA, but just inform the users of your results that the homogeneity of variance was not satisfactorily. And that would be up to you. Now, these protocols need to be satisfied for the ANOVA to have more powerful meaning. And I call them protocols because there are things that must be established prior to really running with the ANOVA. Now, the first of these, of course, is independence. Independence means that the populations are separate, that one does not depend upon another. My wife and I are not independent because what she wants to do is normally what I do. The other night, I wanted to go to the movie. I love going to the movie. I want to go to the movie. I want to go to the movie. And bless her heart, she didn't want to go to the movie. She had work to do. So in my dependent status, we stayed home. The next night, I went ahead and bought the tickets. And so when she got home, I told her, I said, hey, we're going to the movie. I bought the tickets. So she had to assume the dependent status, and I was the independent. Independence in these data sets means that one is not controlled by the other. So we assume that they're independent. Normality means that we assume that they're normally distributed. If they are non-normally distributed, we call those parametric. and we would use a parametric process, which is something we're likely not going to do in this particular course, but we're assuming that they're normally distributed, and I will show you how to test for that. We're also assuming that they have homogeneity of variance, and homogeneity of variance means that the variances are the same. Let me share with you about normality before we get to the homogeneity of variance. A curve may be left skewed or right skewed. We look at skewness and we look at kurtosis. Kurtosis speaks to whether it's flat or very sharp pointed. And skewness says it goes to the left or it goes to the right. Now, guys, with a normal curve, it is centered in the middle, so the skewness is appropriate, and it meets a particular form. It is not too flat and it is not too sharp. So when we talk normality, we look at skewness with a value between -3 and 3, and we look at kurtosis with a value between -3 and 3. Now, the test also requires homogeneity of variance. Independence means one does not control the other. Normality means that our skewness and kurtosis is under control and that our populations are approximately normally distributed. Homogeneity of variance means that the curves have the same size standard deviations. In other words, we don't have something like this, one with a narrow standard deviation, one with a big wide standard deviation, and one with a somewhat normal standard deviation. In other words, the curves look somewhat similar in how that they are distributed. Now, ANOVA should follow the following steps. First of all, we're going to collect the descriptives, including the skewness and kurtosis. Then we're going to conduct the ANOVA to determine if significant difference is present. If difference is identified, we will conduct a post hoc test. The Tukey test is recommended, though there are many other forms that are all valid. And then we're going to interpret the post hoc using the descriptives. Now, let's start just a second with this idea of collecting the descriptives, including skewness and kurtosis. If you will recall, when we did the difference in two means, we had to put the data in different ways to actually get the descriptives, and then we put it inserted it in SPS in another way to conduct the difference of two means. We will do the exact same thing when we do ANOVA. Then when we conduct the ANOVA, we will put the data in showing a variable of group and a variable of values. And then if we identify a difference, that the means difference, then the post hoc will allow us to look at where that difference exists. Now, I want you to think about it just a moment. If the post hoc test tells you where the difference exists, it assumes, first of all, that you have difference. If you do not establish difference, you're through. There's no reason to proceed and do a post hoc test. And then once we get the post hoc test and we find out where the difference is, we have to interpret it using the descriptives. Now, here's a sample problem that we're going to work in just a moment. We have resistors that are produced by 3 different vendors. Now, assuming that all other things are the same, we might be trying to find which one of these is best using a t-test or using an ANOVA. T-test, we compared 2. In ANOVA, we're going to compare 3 or more at the same time. So vendor 1 is independent of vendor 2, is independent of vendor 3. I don't want you to panic yet. You've got this. This is not as difficult as it sounds. It's just a process that you flow through. You start out you establish your protocols, and once you establish your protocols, you have your 6-step plan. We're going to do a sample problem, and you're going to make a conclusion, and you're going to write it up in a statement. Don't panic. You've got this. You're moving right on up the ladder, and I'm very proud of you. Very proud of you. You're doing very well.